All right. Next, I am super thrilled to introduce Ines. Ines is a engagement manager at QuantumBlack, McKinsey and Company, where she leads a team of data scientists, engineers, designers, and business experts to develop machine learning powered products and shape data and analytics strategy for some of the world's biggest organizations. Today, Ines is going to be talking about algorithmic fairness from theory to practice. She'll be talking about recent advances from the ML research community on fairness, including detection of bias in data, assessment of fairness in ML models, and post-processing methods for model predictions to achieve fairness. Take it away, Ines. Very excited for this talk.
Hello, everyone. It's great to be here today. My name is Ines, and I'll talk to you today about algorithmic fairness from theory to practice, and I'll discuss some of the recent advances in the field of algorithmic fairness coming from academia, but also I will provide a practitioner's perspective in terms of how these advances are being applied in practice across a variety of industries. So I think algorithmic fairness is one of these topics that I'm sure I don't need to motivate too much. I would imagine most of you are aware of just how important of a topic it is. But just to set the stage a little bit, I think part of the reason for its importance comes from the fact that machine learning today is used to make many key decisions. And there's a few examples here on the slide. So we have decisions in car insurance in terms of a driver's risk score. We have loan approval decisions, parole decisions, employee performance, and job applications. So in all of these areas, and these are all very consequential decisions, these are decisions that can impact someone's day-to-day life, or in some cases, such as parole decision, alter the course of someone's life. So machine learning is making these and other increasingly more consequential decisions. This has been going on for a number of years now, and there's every indication that this is going to continue, if not accelerate, in the coming years. And in fact, if we polled the audience here, I'm sure you could come up with many other such examples where we have consequential decisions made using machine learning right now. So given how much we rely on algorithms for these very important decisions, it is very important to ensure that these models that we use do not discriminate on the basis of sensitive attributes or protected categories. So these are things that include race, gender, age, religious beliefs, but there's a lot of other such attributes. And in fact, there's no complete list covering all of them. And the unfortunate reality is that the data we often use to develop machine learning models contain societal biases. And it's therefore really important that machine learning models we use do not replicate or even worse, exacerbate these biases. So to understand whether bias is occurring, especially when decisions involve people or policies, the outcomes should definitely be checked. And this is where the field of algorithmic fairness comes in. So what do I mean by bias? Well, at a high level, perhaps a simplified way of looking at it is in terms of direct bias versus indirect bias. So direct bias refers to situations where we have sensitive information or protected categories that are explicitly used in the modeling to make a certain decision. So it could be a model that predicts law school admission based on race as one of the criteria. Arguably, a lot more pervasive and difficult to detect is the other category, which is called indirect bias, indirect discrimination, where seemingly all the features are neutral, are non-sensitive, but still we end up with different outcomes for individuals across different groups. So another example could be the use of a zip code of an individual to determine loan approval. So you could have a model where all the features are neutral and non-sensitive, yet you get different outcomes. There's another way we could look at sources of bias, and this is based on where in your data collection pipeline it occurs. So the first, the first category of that bias is what we call collection bias. So this is referring to the actual process of collecting the original data points. So which data points were recorded, measured to begin with, because only the data that is measured can be included in your model. Then we have the reporting bias. So this is the bias in the frequency at which the data is reported. So for instance, you could have a situation where certain data points are recorded quite frequently, and you need to make a decision as to how you want to represent this in your modeling, whether you want to have weekly or daily or monthly features. And this decision seemingly seems inconsequential for fairness purposes, but actually it could be quite consequential. Different ways of representing the data, choosing to look at, for instance, weekly granularity, choosing to look at the days of the week, Monday to Friday, versus looking at the weekend, versus choosing to look at an observation on a daily basis. These decisions could have different consequences for different subpopulations. Then we have our selection bias. So this is bias referring to all the available data that you have collected, reported, you have available, and which decision do you take in terms of which subset of the data do you select for your modeling. So in case data is selected in such a way that it does not reflect the true distribution of the data in the real world, this could be another source of bias. And finally, there's what I call here annotation bias, but this is really referring to any time that we have some type of manual curation of data, where we have actual people either labeling the data or manually curating it for further processing. There could be mistakes introduced due to human error, and there could be unconscious human biases that go into this labeling of data. So how do we prevent this from happening? Well, I would like to think a little bit about the typical life cycle of building machine learning models. And this slide here is kind of highly simplified, but I think it paints the picture of a kind of maybe typical project. Let's say you have a 4-month project to do some type of a machine learning model for, loan approvals or another use case. So we typically start on a project by preparing the data for modeling. Then once the data is sufficiently prepared, we build the models. We do a couple of iterations to optimize for our chosen performance metric. This is quite an iterative process, so we may iterate on the data, iterate on the features, on the choice of the model. And at some point, what might happen is we remember to check for fairness. So it could be, month 4 of your 4-month project, and you decide to check for one of the fairness metrics. So for instance, you may select equal opportunity. So this is a group fairness metric that I will explain in a bit more details in a minute. And you realize that you're actually not doing that well when you take into account equal opportunity as a metric. Your model seems quite biased. Even though the overall model performance, maybe let's say its accuracy is fine. The question is, where do you go from here? You've already spent a lot of time developing this model. So it's really hard to know at this stage, if you think about this always towards the end of the project, whether this was your model choice, whether this was your features, the data itself, or was it even the way you formulated the problem? Was it the case that you were trying to answer a question that was fundamentally not amenable to be solved by machine learning? It's really hard to know which stage of that overall product development pipeline should you go back and fix. This is why something that I have found quite helpful in my own work is treating fairness as an iterative process. It's something that needs to be emphasized at every stage of the model building life cycle, rather than just treating it as an afterthought or something that happens towards the end of the product development life cycle. So this could look something like this, and this is just an illustration for what some typical steps may be. So in stage 1, we have the data preparation step that I talk about. But as well as doing all of your usual steps, we may also check the data for bias. We may check that all of our relevant subpopulations are well represented. We could check, for instance, for that selection bias, did we really select a well-represented data set? Are we covering all the relevant populations on which the model will be deployed. Which features are we using? Then we go to step 2, we build our machine learning models. We have a chosen performance metric, could be something like accuracy, but we may add some regularization for fairness, or we may not. But either way, it's important to inspect already in the very early model iterations whether you have balanced outcomes. And if outcomes are unbalanced, then we can continue to step 3 here, where we run diagnostics. So we have metrics which measure the amount of fairness. And I'll discuss those in a couple of minutes, but it suffices to say that there's many dozens and dozens of different fairness metrics. And here we may select one or a few that are relevant for the problem at hand and check it. And so this could be, already only a couple of weeks into your project, but it's really important to check already the early iterations of your model, because then you can decide what you do next. You can either go back to step 1 and work on the data itself. So you can do more data cleaning, data pre-processing. You may realize that actually you're missing a portion of the data, and so you go back and collect more data and have a more balanced and well-represented data set on which you build your model. You may realize that you're missing some really important features that allow you to really make accurate predictions for everyone. Or you may realize that there's some features that are actually not appropriate to be used for the problem at hand, so you may drop some features. You continue this iteration, and at some point you inspect the results and realize that the output is both, accurate if that was the metric you chose in terms of your model performance, but also it performs well for your in terms of your chosen fairness metric. And so this process, takes a lot of time, and it's often not easy to achieve both good performance and fair outcomes. But I think this puts you as a developer in a really good position where you, by checking fairness at each stage of the model development lifecycle, you're able to actually really well zone in on a particular stage of your product lifecycle and tackle a really specific part of the problem, rather than reaching the end of the product development lifecycle and having to think about all the previous stages and what could potentially be improved. I have talked a lot about inspecting bias, measuring bias, checking for bias, but what does this actually mean? How do we actually measure bias? So there's actually many metrics. I could spend half an hour just listing all the definitions now, but I will try to summarize them and categorize them into a few categories that I find quite helpful when thinking about what are some metrics available at my disposal. So one way to measure bias is based on bias in the data. So the question is, what is the level of bias in the data that we use to train our models? So the first way we could measure bias in the data is based on feature exclusion. So we could say that, well, our data set is fair if it does not include any sensitive attributes. And this is actually not sufficient to ensure fairness due to a number of reasons, including, for instance, redundant encoding, where a certain neutral, seemingly non-sensitive feature correlates a lot with one of the sensitive features. So the features that we do use can still contain some information about the sensitive attribute. You could remove then those features as well, but at some point, by removing too many features, we could really harm the predictive power on any model that's trained on top of this data. So for this reason, a more widely used way to measure bias is based on non-sensitive features. So we still need our sensitive attributes to define groups. So let's call them minority and majority group. Let's consider two groups for simplicity here. There's a number of metrics that allow you to measure and have a single number that indicates the level of bias in your data set. So if we are talking about a classification problem, there's metrics like impact ratio, where we may look at ratio of percentages of positive observations in the minority versus majority group. And fairness would mean that the two percentages are similar, and therefore their ratio is close to 1. If, on the other hand, you're talking about a regression problem, you could use something like mean difference, which measure the differences between the means of the target in your two groups, in your minority and majority group. And if your data set was fair, you would expect these two means to be quite similar, meaning you would expect their difference to be close to zero. Then another way of measuring bias, the second big way, is to look at the model itself. And here we can focus on the fairness of the decision outcomes, which is where the majority of the metrics fall under, or we can focus on the fairness of the decision-making process. So let's first look at the left-hand side. The fairness of decision outcomes looks at how fair the model outcomes are. And we can look at this in two major ways, at the individual or group level. So individual fairness metrics require individuals who are similar on all the attributes that really matter for a particular decision. So for instance, if we are talking about the job application use case, you would think that prior work experience would be a relevant feature. We would want all such individuals who are similar on all the features that actually matter to receive similar outcomes, regardless of their sensitive attribute. And there's a lot of metrics within that individual fairness space. On the other hand, we have group fairness metrics, which are arguably more widely used in practice. And these group fairness metrics, and again, there's many specific metrics in that category, require the model to behave in a similar way for all groups of individuals. So if we compare two groups, minority versus majority, or you have several groups defined based on sensitive attributes, we want the model to behave in a similar way. Rather than focusing on decision outcomes, another way we could think about it is fairness of the decision-making process that leads to these outcomes. So this is called procedural fairness. So this notion of fairness is based on fairness of particular features in the decision process based on their reliability, privacy, and actionability considerations. And they depend a lot on the background knowledge about the input features as well as the societal context. So I've talked a lot about detecting and preventing bias, and as kind of my last topic for today, I want to talk a little bit about techniques for handling bias. In other words, if you have an existing model and discover that you're making biased decisions, which steps can you take to improve this? So again, this is an entire research discipline unto itself, and there are three big categories of bias handling techniques based on the three different points of intervention available. So you can intervene in the data set, in the model, and the model outputs. And this maps to these three categories of bias handling techniques. We have our pre-processing techniques, where we in some way transform the data set to remove the bias. We have our in-processing techniques, where you transform the underlying model, the underlying algorithmic technique, to be more robust to any bias that's coming from the data. And finally, we can change model outcomes to make them directly more fair. So these are called post-processing techniques. And they're widely used in practice, especially when it might be costly or too time-consuming or impractical to change a data set or a model. This might be situations where, for instance, you join a project and the previous developer left. And so it might actually be easier to apply post-processing techniques than to change the underlying model or the underlying data set. And there's a lot of very specific techniques that I don't have time to go into here, but each of these are a research discipline unto itself, and we have a lot of techniques coming from the algorithmic research community that I think are very helpful for practitioners to think about in each of these categories. I will give the flavor of what this could potentially look like in practice by considering a banking use case. So one example of a consequential model might be a model that recommends to relationship managers which products their customers may find helpful or relevant. So what often happens is on projects like this, we may start with a simple linear model that's quite explainable, where we understand exactly what's happening, including being able to check for any bias. But we typically end up selecting something like a random forest, a nonlinear model, which outperforms some of these simple linear models. So to understand the level of fairness and to help us achieve fair outcomes, we can actually apply a lot of techniques from explainable machine learning to provide transparency into how the model is making its decisions. So the first application could be finding models' blind spots. So we could produce cohort-level explanations using post-hoc explainability techniques such as SHOP to help us uncover systematic errors. For instance, if the model is systematically making mistakes in subpopulation. And if we incorporate this early on in the model development lifecycle, it's really easy to go back and fix it because if you spot it early, it's much more easy to spot where the specific problem is coming from, rather than doing this quite late in the process. Another theme is bias prevention during model development. So we could look at cohort level explanations for minority versus majority group to help us identify which features are needed to correctly classify the samples from the minority groups. This can help us ensure that these features are not excluded as part of the feature selection step, because you could be in a situation where you have certain features that perhaps would have been excluded if you performed the feature selection step overall, just selecting top and most important features. But if you do this type of analysis and see that, well, actually this feature is really relevant for this subpopulation that could be the minority of your overall data set, that could mean that you end up keeping that feature because it's actually really relevant for that subpopulation. So this is how we can prevent and treat bias during model development. So I'm going to now briefly recap. I hope I've convinced you that fairness is really important to consider in the life cycle of your product development, especially when the use case is consequential, and many use cases these days are. To assess fairness, there are different methods. There are methods for detecting bias in the underlying data, as well as evaluating bias in the model itself, in the decision-making process, and in the model outputs. To deal with any bias issues, we can focus on the dataset itself, in the modeling, and in the model output. And there's many techniques in each of these categories, and which technique works best really depends on the problem at hand. So I'm going to finish with some takeaways that I hope will be helpful to you if you're thinking about applying algorithmic fairness in your own work, especially in various practical applications. So I think there's really a need for interdisciplinarity, both within machine learning, looking at domains such as explainability and causality, and looking at some outside domains, so looking at law, ethics, economics. Another takeaway is really that there is no silver bullet, and many solutions will be specific to the industry you're considering or to the use case. And there is really a need for collaboration, in my opinion, between machine learning and domain experts. And finally, fairness cannot be treated as an afterthought when building machine learning products. It needs to be emphasized at every stage of your product development lifecycle. So with that, I'm going to thank you and very happy to take any questions.
Thank you so much for that amazing presentation. It was definitely great to learn a bit more about that and what's going on. I know we have a couple questions from the audience that came in. So the first one here says, I am new to algorithmic fairness, but very interested in learning more about the methodologies to see how I can apply these in my work. What are some good resources to learn or keep up to date with literature?
Sure. So that's a great question. I think there's some obvious ones like blog posts and just following some of the more high-level summaries. But I actually think it's really helpful to sometimes dive a little bit deeper and go to some research conferences. So for instance, when I was doing my PhD 5 years ago, fairness, you would have maybe a couple of papers at the conference, but now big conferences have entire tracks dedicated to fairness. I think there's so many great talks, like at ICML next week. So I think conferences, for me, I really enjoy having a couple of days to just deep dive. But as well as learning about fairness, I also think reading kind of about material in related areas of machine learning, like explainability or causality, is super helpful to get a big picture view about how to really apply these solutions in a robust way in practice. And finally, I think it's super helpful to learn about the domain. So this is not necessarily about fairness, but I think you will be able to have a much broader view of fairness if you also know the business context of the application in which you're deploying your machine learning solution.
It definitely sounds like some question here is, what do you do when you check the results of a bias metric and the numbers don't look good?
Yeah, and another good question. I think in my talk, I really emphasized the need for including fairness as part of your model development and checking for it. But actually, it's sometimes hard to know what to do if the numbers, don't look great. And I really recommend looking at your pipeline holistically. So checking for that, let's say you picked a model metric, checking for that metric, but checking for actually a broader range of metrics. I think there's so many metrics you can potentially track, and I think sometimes, you want to keep a few that are high priority. But in cases like this, where you're diagnosing what actually went wrong, I think it's helpful to check a few other metrics that maybe weren't a core priority, but just to diagnose the problem. And I always recommend looking at the broader business context and really seeing, okay, what are we trying to solve for here, and what is the desired outcome, and what does that mean, and what is it about the way we set up the problem and the overall pipeline that could have caused this issue? Because I think the issue is rarely just kind of locally in the specific implementation. It's usually the way you formulated your pipeline overall. So we're all looking at the bigger picture and just checking a wide range of metrics to really diagnose what is happening.
Awesome. And then I know we have time for one more question here. How do you check for fairness of a model in production?
Again, a great question, and it's one of these things that's very important, and you're almost never done checking kind of the robustness of your pipeline. So this is not just true for fairness, but any other metrics. So even once you've trained your model and you deployed it and you're quite happy with it, you really need to keep kind of inspecting what is happening. And I actually recommend, when checking your model in production, to check for a wide range of fairness metrics. So again, maybe during your development you prioritized one or two metrics, but I think it's helpful to actually track kind of even more, maybe 5 or 6 metrics. And it doesn't mean that you're necessarily optimizing for all of them, but I think it's super useful to kind of check for a broad range of things. Check the data fairness metrics, check the model fairness metrics. And because all of them kind of provide a different view of the problem. And I think that whenever you inspect your model for kind of accuracy or any other performance metric, I recommend checking for fairness as well for use cases where it really matters.
Awesome. Well, definitely thank you again. It was great hearing your talk today and then getting those great answers as well. Everyone, we do have Mohan Mukherjee coming up next, and he is going to be talking about Kubeflow pipelines and its operational challenges at scale. And he'll be joining us from iRobot, so that's definitely going to be a great one as well. So again, thank you so much, Ines, for joining us today. It was great hearing from you.
My pleasure.
Thanks. Have a good one.